This comparison shows the total aggregate bandwidth of low Earth orbit satellite constellations against transoceanic subsea networks. While satellites are essential for remote regions, their maximum capacity represents a mathematical fraction of the total. Between 95 and 99% of all intercontinental data travels underwater. The global backbone is a dense grid of over 500 active systems spanning the ocean floor. This infrastructure consists of highly engineered glass tubes, roughly the diameter of a garden hose, resting completely exposed in the dark, high-pressure abyss. Operating in this environment requires a strict physical and operational bifurcation. Engineers categorize the shore-based facilities and processing hardware as the dry plant, and the submerged cables and deep-sea amplifiers as the wet plant. This separation allows engineers to isolate the extreme digital processing needed for speed from the heavy physical armor required for survival. It is the only way to maintain signal integrity across an 8,000-kilometer analog path. This mathematically optimized physical pipeline forms the literal foundation of the digital world, anchored to the most hostile environment on Earth. The journey of intercontinental data begins strictly onshore, inside secure coastal facilities known as cable landing stations. User IP traffic arrives here via terrestrial networks. Utilizing the Border Gateway Protocol, routers identify the optimal transoceanic path and feed the packets directly into the submarine line terminal equipment. Before this information can survive a 5,000-mile journey, it requires extreme mathematical conditioning. The processor appends redundant mathematical data, allowing the far shore receiver to computationally rebuild corrupted frames. Then, an electro-optical modulator uses 16-state quadrature amplitude modulation to map this binary data onto the phase and amplitude of a continuous wave laser, encoding multiple bits per optical symbol. To scale this transmission, engineers employed Dense Wavelength Division Multiplexing. This technology allows operators to combine dozens of distinct laser frequencies, different colors of light, simultaneously into a single microscopic glass fiber. This extreme digital processing within the dry plant is a mandatory prerequisite. It is the only way to prepare fragile binary information for thousands of kilometers of pure analog transit. Leaving the landing station, the multiplexed light pulse drops below the surface, entering the submerged infrastructure of the wet plant. This cross-section reveals the protective layers. Outer polyethylene and steel armoring surround a copper conductor, completely shielding the hair-thin silica glass fibers at the center. Once in the deep ocean, the system faces an absolute constraint. Digital electrical regeneration is impossible mid-span. The signal must remain entirely analog as it travels across the abyssal plane. To combat the natural attenuation of the light, submerged repeaters are spliced into the cable every 60 to 80 kilometers. The exact mechanism driving these repeaters is the Erbium-Doped Fiber Amplifier. An internal pump laser continually excites erbium ions suspended in the fiber. When the degraded communication signal passes through this section, it triggers stimulated emission. The light absorbs the energy and emerges massively boosted, without ever being converted back into electricity. Powering this continuous chain of amplifiers requires immense electrical force, generated by shore-based power-feeding equipment. Operators push high-voltage direct current, up to 15,000 volts, down the cable's central copper conductor. The seawater itself acts as the electrical return path, feeding power to every repeater across the transoceanic chain. The wet plant is a triumph of sustained optical physics, engineered to amplify pure light for a 25-year lifespan under extreme hydrostatic pressure. As optical transmission approached the nonlinear Shannon limit, upgrading older modulation algorithms became highly inefficient for scaling capacity. The physical hardware solution currently dominating the industry is Space Division Multiplexing. Space Division Multiplexing maximizes total system capacity not by optimizing a single fiber, but by drastically increasing the number of parallel fiber pairs and utilizing shared pump lasers. Modern cables built with this architecture routinely achieve aggregate capacities exceeding 100 terabits per second. A major bureaucratic shift accelerated this hardware rollout, the adoption of the ITU-T Open Submarine Cable Standard. This established true disaggregation, allowing operators to completely decouple proprietary dry plant terminal equipment from the wet plant repeaters. Eliminating historical vendor lock-in drastically lowered the barrier to entry, triggering an economic inversion in who controlled the network. Cloud hyperscalers like Google, Meta, Amazon, and Microsoft require immense bandwidth to synchronize their global data centers. Instead of leasing capacity, it became cheaper for them to finance, build, and fully own the majority of new intercontinental routes. Standardizing the physical hardware interfaces allowed a few massive software corporations to usurp national telecommunications consortiums and privately rewire the physical internet. Despite this massive investment, the infrastructure is fragile. Operators constantly pull the system from the landing stations, monitoring the optical signal-to-noise ratio and mathematical Q factors for the slightest signs of degradation. Deep in the wet plant, the system faces unique chemical threats. Electrochemical corrosion generates dissolved hydrogen. If these molecules permeate the glass core, they absorb optical energy, causing irreversible signal attenuation, known as hydrogen darkening. Voltage gradients cause electrical trees to branch through the polymer insulation. Upon reaching seawater, they create a shunt fault that violently short-circuits the power conductor. However, 80% of cable faults occur in shallow waters, resulting directly from violent impacts by dragged commercial ship anchors and heavy fishing trawlers. Engineers attempt to mitigate these physical hazards during the planning phase, using advanced computational path planning algorithms like the fast marching method. Older Dijkstra algorithms forced cable paths to adhere to rigid grid edges, resulting in suboptimal, jagged routes over steep ridges. By solving the eikonal equation, the fast marching method replaces rigid grids with a continuous path that smoothly hugs uneven 3D bathymetry. Operating a subsea network is a paradox. It requires balancing mathematically perfect optical physics against the chaotic, unpredictable hazards of the maritime environment. Zooming out to the macro geopolitical map reveals how shortest path routing creates severe geographical choke points. This satellite view shows the Bab al-Mandab Strait between the Red Sea and the Gulf of Aden. Roughly 90% of all communications flowing between Europe and Asia is funneled through this narrow body of water. Concentrating massive capacity here leaves the global economy exposed to accidental disruption and asymmetric sabotage. The Smart Cable Initiative is now expanding the function of this network by integrating environmental sensors directly into the existing physical infrastructure. This project integrates ocean bottom pressure, temperature, and seismic acceleration sensors directly into the metallic housings of the deep-sea repeaters. This hardware addition transforms the commercial internet backbone into a planetary-scale scientific observatory. It provides persistent deep ocean data previously impossible to acquire, establishing a real-time global tsunami early warning system. Every alternative to this system hits a mathematical ceiling. The efficiency and aggregate capacity of transmitting modulated photons through solid silica gloss mathematically dwarfs the physical limits of broadcasting radio waves through the atmosphere or the vacuum of space. Until the laws of physics change, the dark, highly pressurized bottom of the ocean will remain the indispensable, hardwired foundation of the digital cloud.